Good morning, ladies and gentlemen. As Ingo said, I'm at ÖBB Rail Infrastructure, responsible for lifecycle management of all track assets uh, here in Austria. And today I want to talk about operational lifecycle management of railway track assets, and how we deal with this topic at the Austrian rail infrastructure, and give a little bit an insight into our LCM software that we use and that we use for especially for our track assets at the moment. For those who don't know it, not many, but I think who don't know it, we are the rail infrastructure manager of Austria and part of ÖBB Group. Uh, Besides Personenverkehr, passenger transport, or rail cargo, and some subsidiaries. Uh, we plan, build, and operate and maintain the Austrian rail network with approximately 19,000 employees, uh, 7,000 trains a day, 278 million passengers a year. And these 71 railway companies on the network and seven rail freight terminals uh, protect the climate together with at the moment, eight hydroelectric power plants. But what's the content for today? I want to cover the whole lifecycle management and draw a little bit the bow from the engineering part via a costing part and towards to a applied lifecycle management, and to finalize with a short insight into our IT tool that is calculating our lifecycle costs. It is called LCM Assistant. So I want to start with what is lifecycle management, or better, what is our definition for lifecycle management at ÖBB Infrastruktur? We have some kind of three dimensions of lifecycle management as an overall view. We start here with the basis. The basis is the engineering part of the life cycle story. It's the life cycle engineering. It's based on measurement. It's based on technology and innovation, norms and standards as well. But also, and especially, there's much experience and know-how inside the life cycle engineering. And here we result in the asset behavior. The asset behavior is the end of the basic end of the technical part in describing the life cycle of the asset. And after this life cycle engineering, we come to the economic aspect, to the uh, economic evaluation based on life cycle costing. So here we have the costing aspects of the life cycle. We have maintenance costs and especially renewal costs, and we have costs of unavailability of the asset, the system, so-called the costs of operational hindrances. So far, this uh, has all been based on one asset type. Uh, we come now to the evaluation across the assets. We add synergies in construction management and uh, optimize the availability of the assets uh, when when we combine the several construction sites. And all in all, we guarantee with this LCM approach for sure safety, but also optimize the availability and the economic efficiency. So this is our three dimensions of LCM. And now I want to go into each of them to describe a little bit more what we deal with and what this topic and the theme deals with. We start with the lifecycle engineering. We're getting so closer to the technical part. Uh, and the results of this lifecycle engineering will be we get the technical condition forecast for components and parts, and we get a prognosis of maintenance measures, maintenance actions. But how do we get these results? Let's see. We have modern inspection options. A lot of experience and know-how is added by these things. Uh, we inspect our assets with our own experts. And example here from structural engineering. Here's a defect documentation, a crack log, and we have location and inspection planning. And we have crack detection and time series with these cracks. We have these applications for smartphones, tablets, laptops in our cloud, and uh, this is an input for our data analysis. Then supplements to the established measurement methods in track technology with our own measuring cars, uh, are commissioned according to the specifications we do, and we focus there more and more on artificial intelligence on the track to deal with high-speed videos for track components, uh, error detection with image recognition, and we receive a component deterioration with this artificial intelligence. Uh, Afterwards, we analyze our data. We analyze our measurement data ourselves. This is important for us. We have self-developed measurement technology platforms. We use the correct positioning to get the right time series. Isn't it the basis for a correct time series to get the right positioning? And we have all our separate tracks with GPS coordinates that we can assure a correct deterioration. We have other data measurement analyzing tools, dashboards for visual analysis by our technicians with different views and layers and, and zoom levels. And uh, as an example for wide ranges for evaluation, here the correlation analysis between measurement signals. Then we come to the most sophisticated part of the maintenance uh, data analysis. It's the predictive, the prognostic maintenance. We go from the data sets to forecasts and maintenance measures. So first of all, we have a component condition. And then we come to a component deterioration. This is more important than the condition because it's important if the condition tomorrow is bad or tomorrow is as good as today. And then this is the real sophisticated part from the deterioration to the real maintenance action in the predictive maintenance because it's uh, different to just go via a condition that is over some threshold than to do the real planning of a construction site. There are boundary conditions you have to include into your planning. So this is the most sophisticated part of the predictive maintenance. And we carry out this maintenance planning ourselves. So more and more with digital support. I don't say that we use artificial intelligence for everything, but we more and more use these uh, framework and this support for planning our maintenance actions. And this is maybe to so to say the end of the real technical part of the life cycle story, because we come now to the costing part of the life cycle, to the evaluation of the previously mentioned measures. So we define technical and economic evaluation based on life cycle costs. The technical part was the base was is the technical part, and now we do the economic evaluation uh, of this life cycle. This is the result of the economic evaluation of the asset life cycle. How does this look like? We go from the technical to the economical part. So we base, as I said, on the technical part. Here is the technical view from uh, before again. And we have, for example, here separate components. So the rail and the sleeper, there are many others, but as an example, two uh, components. Uh, and here again, the condition and the condition over time. So the deterioration and the maintenance measure to repair it. So a sleeper exchange or rail exchanges here and here. And here you can see the respective costs that occur per year in the life cycle. Here the renewal and here the maintenance actions that will rise in the end. Uh, but where is the point in time where we should renew this from the view of life cycle costing? In which point of time it's better to not maintain anymore, not repair it anymore, but to renew uh, the track in this example. Here are the corresponding life cycle costs for this life cycle. And you see the LCC rise in the end of the row. And here you see, you get here before the start of the rise is the optimal point in time for the renewal of this track section. For sure, not later than this part. Much later, you have to analyze it, but not in the years afterwards. This is basically a boundary, uh, but also not too uh, too early. Here, these years are the best renewal time for an exchange for this asset group. And now we come to the maybe supreme discipline of the lifecycle management, the optimization across multiple assets. We combine several construction sites and get, as a result, synergies in construction management and optimization of the asset availability. Uh, what is lifecycle management? Yeah, and why at this moment? Because now, to describe it in more detail, uh, here is a graphic for the so-called overall approach. Uh, till now, we had just a component approach or asset type specific approach. And now we have here an overall approach. We have catenary, we have supporting structures, and we have cable and safety systems, we have track, uh, and we combine these asset-specific lifecycle views in the overall LCM concept. So the lifecycle engineering part and the lifecycle costing part is done within each asset type. And now we combine it in an applied lifecycle management and overall approach at our lifecycle management model. So I mentioned before the basis of LCM optimization is therefore recording of all measures on a specific route on all assets uh, in terms of time and in terms of the extent of the route. Uh, in practice, not only the renewal or the reinvestments play a role, shown here in blue, but also the regular maintenance activities shown in yellow. Uh, a next step is to identify possible track closures. If we have them already, we can put it into our model or into our system. And with the building blocks we had, the building blocks of lifecycle management, uh, this uh, LCC per asset type. So our LCC per, as we heard before, the costs of operational hindrances and the synergies all combined result in the overall view, in our overall view, to get the technical and economic optimum in the overall system. How do we achieve this in practical? We calculate our life cycle costs of our asset with our integrated planning tool. I said it in the introduction. This is called LCM Assistant or Lifecycle Management Assistant. There are dashboards with tracks and planning periods, display of the individual LCC at that section. But more here in a quick look at some of the evaluation levels of the tool. After the entry screen, we start in a map with all routes of the network. And in addition to some other many search functions we have in our tool, we can also click just on the route and get some kind of route or a track tape with all assets. We have here to point out and point in tracks. This is the track 1 and track 2 of this section, or of this route. The switches and catenary, bridges, walls, and we have noise protection, but there's no noise protection in this example. We have railway crossings, railway crossing safety systems, especially here, uh, platforms, drainage, uh, pipe, pipe passages, so to say, yeah. And not on the screen and in the route, the control center and the area of the control center. And below this route or track tape, uh, the LCC optimal times for renewal of the assets appear in this planning period from this year to our frame boundary here in gray and afterwards. So for the example, we can tick here an asset. Here, for example, a track section with an optimal point of time of the renewal in 2037. It's just an example to get a look on the um, functions of the tool. And if we click and go into this asset, we get the LCC function of this asset with this corresponding LCC optimum in 2037. Besides, all assets in the network have a calculated LCC function in the background. It's about 250,000 assets that are basically calculated with an LCC function for the technician, for the user of the tool. And now we come to the evaluation across the assets. So it's the LCM analysis. Uh, we can see here the optimal time for renewal of these assets with the minimum life cycle damage. We call it life cycle damage. Uh, for the details, formally, according to this system, the damage here in the individual measure optimum is green at the top, but this is only a theoretical. In this example, we have here practically using the factor minimum in this year with the minimal damage, uh, just for questions. And this minimal damage compared to these higher damages here, we have more or less zero damage, and here an index and a damage index with 40, 50, and more. So this is our basis for the evaluation across the assets, the LCM analysis. And here another view at this LCM result within this time row. Again, here the optimal point in time for renew this asset. And now it's possible for the asset engineer to directly transfer the project into the approval process. And we start here the challenging process of the project within these results of the LCM analysis. But this is another story. Okay, to conclude my short overview, what do we need for modern lifecycle management? We need modern inspection options. We inspect our assets with our own experts and own measuring cars. We do data analysis. We analyze our measurement data ourselves. We do predictive maintenance more and more with digital support, and we carry out our maintenance planning ourselves. And we bring it all together in an integrated lifecycle management. And we are convinced that this is the key to system optimization for lifecycle management of railway track assets. Okay, then thank you for the moment. And if you have any questions, don't hesitate to ask.